Okay. So, welcome you all to the next lecture. In the previous lecture, we gave the example of an autonomous perception function, also the planning and actuation function using a commercial or civilian example of which is called as autonomous driving, which is a very kind of popular in popular technology thing in today's area. Today, we will be extending the same concept using a military kind of application or a defense application using UAV based maritime surveillance test bed. So, if you see in this example, suppose you have a maritime band, you can take any maritime band. Now, you know all this Iran wars and everything is happening, and your Hormuz Strait is blocked by Iran due to they won't be able, there is no ship is passing, we are all facing these problems and all. Okay. So, suppose you want to see there is any kind of, you have suppose want to surveil in any kind of a sea band or not. Okay. So, what you will do? You do not have a manned platform, you want to have some your MALE or MALE means medium altitude long endurance UAVs, or you have a set of say HALE platforms. HALEs means high altitude long endurance UAVs. With this, you would like to kind of surveil the area. So, you can see in this kind of just a pictorial view. So, it is a maritime surveillance. So, in a maritime environment, there could be multiple ships are coming here and there, going and all. So, you can see these are all kind of multiple UAVs are kind of operating, okay, in a particular zone. So, what are their now? What are their sensors? They have their radars. Obviously, in such a, if you want to scan such a large area or so, you need to have a radar. Without that, you cannot do. And once the radar is picking the target, then and if the target is kind of confirmed your kind of a threat or not, then you will deploy another sensor which is called another UAV which is equipped with a EOIR payload, and that is kind of going to a close look onto the target. And if the target, it will track the target till certain time, and if the target is assumed to be a threat which is not of your interest, then you decision to kill it. Okay. So, this is that kind of system. So, you can see this diagram. So, you have seen that there are a lot of kind of ships and all, and normally each and every ship which is operating in a kind of in this kind of shipping environment, they must have something called AIS. AIS means automatic identification system. So, AIS information is must for the ship. If some ship is not having AIS information, that means he or he is switched off his AIS, that means he or she is hiding his identity. So, that means it could be an enemy ship, it could be a red ship, and and if its behavior is not a kind of great or something mischievous he wants to do or something like that, you would like to ask your UAV to go to monitor continuously the ship movement, and if it is convinced that it is going to do something, you would like to neutralize it by dropping a bomb, or you send your warship to take on that hostile target. Okay. So, with this just I would like to show you some kind of a block diagram. The block diagram is not very important, it is just a maritime surveillance system simulator model. So, it is an UAV based simulator model. So, in the simulator model you have a lot of say UAVs. UAVs what if you want to simulate this thing, suppose in as a system of systems. So, you have your UAV models, your flight dynamics and kinematics and guidance, all these models, plus you have a set of payload models. What are the payload models? It could be your radar, pulse Doppler radar, it could be your UIR sensor. So, you have your sensor models, you have then your perception function starts here, tracking, classification as well as data fusion. So, this gamut first level of this thing is starting here. Now, suppose those tracks where it will go, UAVs will send it to your ground control station where your armed forces or naval forces is sitting. So, this is actually your ground control station. So, using the payload information, it is coming to the ground control station. In the ground control station, so you have you deployed, suppose to monitor the target, you deployed your radar, you deployed your UIR, or primarily these two sensors, plus you could have something coming from your from GPS as well, some satellite information also. You fuse here everything. Once you fuse these informations here, and then then you have two major blocks. One is called the situation assessment and second is called the threat assessment. Situation assessment means you would like to visualize the situation based on multiple sensor data. What is the possible behavioral intent of this target? And if it perceived to a threat, how you will assume the threat? So, threat means suppose this is your say your interest, your target of interest. With this say this much kind of a bands are there. So, this is actually say when the ship is about to cross this, that means it is actually this is your actually no man's land. You do not want your ship this intruder to pass into the no man's land. What you will do? You will obviously take an action against it. Okay. So, when it is situation, what is the course of the ship, where it is heading and what kind of this thing is there. So, everything is kind of monitored using the situation awareness, and when it is understood that it could be go to a kind of this thing to your no man's area, then you would like to shoot it down. Okay. So, here now I will tell the thing as the observe, orient, decide and act. Observe means you are now observing continuously using your sensor, your radar, your UIR payload mounted on a UAV, you are observing. Orienting means target is also changing its course. You also need to plan your path or UAV path accordingly, so that you can have a continuous look, continuous hawk eye onto the target. Okay. So, this is your orientation. Okay. Decision is here in your ground, where all the target information, processed information, the tracking. Tracking means it's what is moving target, what is this kinematic information, position, velocity, course, heading, yaw rate, everything. This is your tracking. So, you are doing the tracking, you are continuously following the trajectory of this by your sensors. Radar gives one track, UIR gives one track. With those two tracks, you are merging them, okay, and you are trying to infer the situation. The inference is called, then is coming a situation. What is the situation? It's still a hostile target or still a friendly target, could be a friendly target, because you do not want to lose a friend, okay. So, that is called in situation and threat assessment. So, these are all kind of statistical algorithms that we will be talking in this lecture. So, this is called your full kind of sensing cluster. Then final decision is happening using the situation and threat assessment, actually in the threat assessment. So, if it is a threat, decision has done and then you go your actuation. That means your all the subsequent action of neutralization, or you want to give a warning shot, that is your actuation layer. So, this is called military ODA loop in context of your maritime surveillance or in a kind of military application. Okay. Now, we will go little bit change our course. So, last class I have talked about mainly the SPA architecture, of your sense plan architecture for an autonomous driving application, because that I think will be kind of thing, because all of you might be, or most of you at least, or few of you will be kind of knowing the driving. So, you can think how autonomous systems is actually behaving, and then I had told a military architecture in a ODA loop how actually autonomous systems can behave. Okay. Even you can think of your latest Operation Sindoor also. Just let me give one more example for 2 minutes. Even latest Operation Sindoor, what happened? You have your air defense system, and you are from our other side of the half, you have continuous drone attacks, missile attacks on our territory. So, you have to track them. How you track them? You obviously your radar, your camera, your RF detector, all these are deployed in different zones. So, they are kind of looking for the target, which are the hostile targets or enemy targets are coming to our land. When it is coming, then you have your all these our air defense weapons are there. So, for example, your Russian S-400 plus your Akash Tir for the Bell, and also if for a small drone, your operator, your army, your personals are there, they can shoot it down. Okay. So, this part is called the action. So, you can see in the air defense also, this entire chain is autonomous. If it is a autonomous this thing, then you can do it through your air defense system like S-400 or Akash Tir, or else you can do it by manually by putting this. Okay. So, up to this now I will change my track little bit on something called what is called data fusion or information fusion, okay, because this is very important. Our subsequent, when we start now from theory, actually from next class, it will be we will might be kind of coming back here when the need arises, okay. So, what is data fusion? Data fusion, as you know, that you have multiple sensors. So, you get the multiple sensors data coming to you and you do association, correlation and combination of this data which are coming from several sensors or from several source into one meaningful quantity. What is that quantity? It is actually your target in position, okay. So, we are very interested of my target position. So, what is my target position or my object position? I won't use the word target because commercially you normally use the word object. So, in ADAS application. So, object position is the first thing, not only position, but other kinematic parameters, obviously your velocity, your heading, these are also equal interest. So, when you fuse all the sensors information using this method association, correlation and combination, you get the refined position and identity estimate of the target. First, the position estimate of the target, identity I will come later. Now, what is called association? The association actually is called when you are kind of multiple data are coming and there could be multiple object. How will you know which measurement corresponds to which target? Radar is not telling you, or your UIR or camera is not telling you. How will you do it? So, which measurement is for which target? That part is a statistical correlation, is called association and correlation, okay. That, or you may not know, the radar is giving me some reflection that could be from no target. So, that we need to know. So, that process is called association. So, whether first thing the measurement which has come, this is a valid measurement or not. If it is a valid measurement, how will I know which measurement belongs to which object? So, that part is done through this association and correlation. We will be telling when we start the target tracking. And then combination. Combination means we are merging these two information in a meaningful way, okay. So, there is another definition by J.D. Hall, that D.L. Hall, that data fusion is a process of combining data or information to estimate the predicted entity states. So, it is a simple information. So, you are combining the informations, okay. Information fusion, data fusion gives you kinematic informations primarily, as I am telling again and again. It gives you your position, velocity and your heading, all these things, okay. Information fusion will give you what kind of class this target belong. In a advanced driver assistance, it is a pedestrian, it is a car, it is a bicycle, or it is a bus or long truck. What is the classification of this? That part is told, or what is the class of target. In a military thing, it is a speedboat or it is a frigate or whatever, it is a small boat with guns and what is the intent. So, this is called to classification information, okay. So, from your sensor data itself, not only through your measurement kinematics, but there are certain thing called electronic intelligence. From this electronic intelligence information, you can actually tell that what is the kind of class of this target is all about. Next, I would like to tell actually the different kind of fusion models are there. So, we know now, you please remember the two things, one is called sense, plan, act or the UDA, both are same, sensing, planning, this thing. Now, when you are doing sensing or you are doing observe, there will be also sub layers. So, that we will be telling here. This is called the any fusion layer, whether it is a military layer or whether it is a kind of a civilian layer. Even civilian layer parts of this thing, not everything, but parts of this thing are applicable when we do the thing. So, level 0, let me start with level 0. What is level 0? Level 0 means your data acquisition, you have a hardware, you have a sensor hardware which is taking the information, or it is a kind of first characteristic. So, that is called your level 0, okay. You gather the data, fine, you send it to your processor, that is called the level 1 processing. Level 1 processing will be what we are mainly interested in this course. Tracking, we will be doing the tracking. What is called tracking? We will be studying in detail. we will be starting telling something called classification and identification. So, what are the different statistical algorithms that are used either in tracking or classification? And also I have not written here, we will be doing some kind of basic fusion. Okay. So, how we merge the two information of this thing. So, these three are, again I am telling, I am repeating from last lecture, these three will be the part of this course. Once we do this, then it comes on the meta level tracking or meta level information processing. I won't use the word tracking, I will say meta level information processing. That is my, in a UDA terminology, what is my situation assessment. Okay. So, I am trying to assess the situation and if the situation is kind of a threat or not. For SPA point of view, this is kind of a planning, you can say, it is kind of a planning. Okay. And because that will decide your next action. Level 4 is actually your optimal, anyway, this is not there in commercial vehicles, but yeah, you can use it. It is kind of called a process refinement. So, how optimally you would like to use your sensors? You would like to use a high power waveform, peak power all the time to track the target, you will be losing power and your cost also of this radar will be kind of too much. So, you have to optimally use the sensors, okay, based on different kind of your electronic budgeting and all these things. Okay. So, that part is called sensor control, that part is called sensor control or level 4, and level 5 is when a human is involved. So, ultimate decision has to be taken and involved. These are all kind of a not fully autonomous, it is there is still certain kind of semi autonomous is there, because human is there at human operator. For example, in a driving thing, it is a kind of a say a driver is involved. Even when you are in a military domain, the example I have shown that there actually some military operator is there. So, his cognitive intelligence is also playing a layer here to in the decision making process. Now, if you want to make everything autonomous, okay, fine. Suppose a robot everything is autonomous. So, you do not need this thing here, you only kind of control your level 0 to level 4 properly, you are done. So, this is called a proper kind of a fusion architecture. Okay. So, this is all about the fusion. So, it depends on now the typical kind of applications, how you would like to do the fusion. Okay. So, with this now I have my introduction is over. So, I will start this thing from next class, but today I will at least try to tell something that well, we will now starting the different kind of first we will start tracking, then we will go on to the classification, and in between we will start the sensor fusion algorithms. So, with this now this course unfortunately it is kind of bit mathematical, but I will try to kind of cover with lot of simulation experiment, so that at least you can, when you simulate using your MATLAB or any kind of or any Python or any kind of a simulator, any kind of scripted language, then at least the concepts are kind of clear. Okay. So, with this now I would like to now kind of jump to our the next thing. First we will start about the tracking. When we start the tracking, we need to talk about little bit on the estimation theory. Unless we understand the estimation theory in our thing, maybe many of you have already maybe have studied the estimation theory, what are the standard tools and standard methods of estimation theory is there, but at least to kind of initiate the continuity of this course, we will be kind of dealing this. Okay. So, first thing that we will be talking is called the simplest thing, which is called least square method. Okay. There are 3 estimation algorithms we know. One is called least square, or in statistical, if it is a stochastic process and all, you can always say it is a MMSE, mean square error, minimum mean square estimation. It could be maximum likelihood estimation, it could be maximum a posteriori estimation. So, we will be telling everything in this course, and we will give the simulation examples, improve your kind of concept. Okay. So, in the least square method, what we will be doing? First, we will be talking about the first order fits. Okay. What is the first order fit? So, suppose you have a constant signal. With this constant signal now you have multiple measurements. Suppose you have the multiple measurements. So, this you have seen, this is your say your constant signal and this cross are your multiple measurements, and you would like to fit it into a kind of a linear curve. So, this is your linear curve, say again say it is a function of time. So, it is y is a function of time. So, a0 plus a1 into t. Okay. So, you have that you have the data. So, now what you would like to do, you want to kind of, when you are doing a constant fit, you would actually try to kind of estimate the coefficients of a0 and a1. Okay. Once in a straight, so that you get a continuous actually you get the equation, basically you want to get the equation. So, we all know from our kind of a statistics or robust statistics that I need to kind of do what is my measurement, my estimation, square of that, a sum of square of that, that is my cost function. Now, there is a two things happening. First, I could do it using this cost also. This is also a statistics, but why I choose a square, sum of square? The reason is, there is a reason, because this is also can give me the same thing. If I minimize it, I can get my, if I do suppose del j by del a0, del a0 equal to 0 and del j by del a1 is equal to 0, and I can solve it, it can give it. But the problem with this is that from your basic differential calculus theory, if I do not give it using a kind of square, it is difficult to differentiate and all. So, that is why as a part of robust statistics, we always go not with the modulus, but with the square of the measured minus estimate. Okay. So, here it is your actually error, we said we term it as a residual. So, when we term it as a residual, so it is your measured, it is your actually estimated curve. So, measured data points minus your estimated curves, and this is your final cost. Now, you solve this two. You do now, you want to do optimal, you want to go get the optimal estimate of this. So, how will you get the optimal estimate of this? So, using del j by del a0 equal to 0 and del j by del a1 is equal to 0. So, once you solve it, actually you will get something like this. Okay. So, this is your sum of measurements up to k1 to n, n is your number of data points, and plus this, and this is your data points. Okay. K equal to 1 to n, k minus 1 into t something, here it will be the thing. So, these are all your time series data. So, this is a time series data. Suppose you are generating now a signal, say a constant, say a signal with some measurements, you got it and you want to do a first order fit. Okay. With this, how you calculate the curve of your a0, a1. Now, if you do some matrix inverse, this thing will be inverted here into this part, you will give you a0 and n1. So, how come, what could be the problem that we will be kind of doing the assignment in the subsequent section, subsequent this thing, what could be the problem that can come here? The problem could be like this. Suppose I can give you, suppose I would like to I can ask you to simulate some signal and you corrupt it with say your some kind of a noise. We corrupt, suppose if you have like this kind of a signal, I will ask you, suppose in this curve you just simulate, corrupt it with some kind of a noise, okay, and you get your data points. Now, I would ask you to just fit it, what would be the best linear fit for this. Okay. Need to write a small MATLAB or Python, some kind of script, basically these equations you need to find, you need to write, you will be given the curve equation, you will simulate the data points and you fit it into a simple first order fit to get your coefficients a0 and a1. So, this could be the first thing. Okay. Now, when you do the fit, now obviously your fit could be of error, it could be of error that my fit is may not giving me the robust kind of this thing or something like that. So, that what is the percentage fit error, that will be kind of interest. So, that will tell you whether my first order fit is good or I have to go for a higher order fit or I have to do it differently. Because see, if my see you have seen this many data points, data point 1, data point 2, data point 3, data point 4, data point 5, point 6, a lot of data points are there. Now, with these data points you made a first order fit. So, obviously, this is your error. This is your error. Okay. So, if your fit is not proper, then obviously the curve that you are kind of doing, you are kind of getting, and this is the first backbone of any tracking or any kind of classification courses. If your fit is improper, obviously you will have a problem. So, this is called the percentage fit error. So, percentage fit error is also something that is important that we need to kind of study. Same thing now I would like to do in a second order fit. So, first fit, as you see here, is called first order fit. There is one more important thing to tell. Thing is that this is a linear equation. Linear equation means you have only in a tracking, if you are doing now suppose tracking, a first order means how many states? 2 states, position, velocity. So, it is similarly your Newtonian equation V equal to u plus at. Okay. Or you can write it if you have the position and velocity. So, you can write it like this way. So, this is a second order, maybe I can remove this. You can say like this. So, x equal to x 0 plus v t, okay, or x dot t you can also write. You can write you can write it say x dot t, instead of v you can write it x dot t. So, you have two states x and x dot, this is very important. So, actually x is equal to x 0 plus x dot t when you have a first order fit. First order fit means you have only position and velocity. X is actually your position, x dot equal to your velocity. So, actually you have two states, okay, x and x dot, position and velocity. With these two is your first order fit. So, you have two states now, position, velocity. When I go for a second order fit, I will have acceleration also will coming into account. So, in a second order fit, how the equation will be? X equal to x 0 plus say x dot into t plus x double dot t square by 2. So, how many states? 3 states, position, velocity, acceleration, and here how many states? Already I have written position and velocity. So, the more and more you increase the order, you will see your percentage fit error is kind of getting reduced. Okay. So, next class we will be covering the second order fit and the third order fit. Also, we will be talking about the percentage fit error, and that will be end of our least square classes, least square estimation classes. Thank you for your time.